What is a treep? As the name suggests, it's a hybrid between a binary search tree and a heap. Now what does that mean? Well, for starters, every node in a treep has two values, a key and a priority. The treep will be sorted like a tree based off of the keys and sorted like a heap based off of the priorities. Keys are the elements you are inserting into the treep. Priorities are randomly generated numbers in between 0 and 1 that are assigned to each element as you insert them. Let's take a look at an example of a treep which is built on these keys and which were assigned these priorities. Okay, so the treep will look like this. As we can see, no parent has a smaller priority value than their child. No left child has a greater key value than their parent, and no right child has a smaller key value than their parent. So, as we can observe, both the tree property and the heap property are maintained. Let's take a look at the search function. Searching in a treep is the exact same as searching in a regular binary search tree. You simply start at the root, and if the value you're looking for is greater than the value of the current node, you'll go to the right subtree and search that. If the value you're looking for is less than the value of the current node, then you go to the left subtree and search that. If the value you're looking for is the value of the current node, then congrats, you found it. If you reach a node with no children, and you still haven't found the value you're looking for, then it isn't in the treep. For example, let's search for 4. We start at the root, and 4 is greater than 3, so we go to the right. It's less than 8, so we go to the left. It's less than 5, so again we go to the left. Finally, we reach the node that we're looking for. Before we continue, I'm going to alter the tree a bit. I'm just going to quickly remove 7. Now we're going to take a look at the insert function. In order to insert into a treep, we must first search for our value. Once we find the location where the value should be, we can insert our value there. But it's possible that the priority of the value is greater than the priority of its parent. In this case, we must check whether our inserted value is a left child or a right child. If it's a left child, we do a right rotation. If it's a right child, we do a left rotation. We continue this until the priority is less than the priority of its parent. Let's look at an example. Let's insert 7 back into the tree. The first step is to generate the priority value for 7. Okay, it looks like we landed on 0.85. So first let's search for where 7 should be in the tree. Now let's go ahead and add it to the right child of 6. But now, the priority of 7 is greater than the priority of 6. Since 7 is the right child, we must do a left rotation. Once again, 7 has a higher priority than 5, so we'll do another left rotation. 7 now has a lower priority value than its parent. Perfect. The treep's properties are upheld. I went ahead and modified the treep again before we look at the remove operation. I'm also going to add this new node, 9, with a priority of 0.42. So, the remove operation works as follows. Begin by searching for your value. Then, as long as the node has 2 children, we check the priority of both its children and rotate in the direction of the child with the lower priority. Once the node has less than 2 children, then it's either a leaf, which is simple to delete, we simply set its value to null, or it only has 1 child, in which case we simply replace it with its child. Let's take a look at an example. I want to delete 8 from this treep. First, we search for it. Okay. Now, for the sake of visualization, let's say that we set the priority to -infinity. This means we want to rotate it as low as possible. Now we have to check the priority values of its children. The right child has the lower priority, so we'll do a right rotation. Now the left child has the lower priority, so we'll do a left rotation. Now the node only has one child, so we can go ahead and replace it with its left child. And there you go, we've successfully deleted 8. You might be wondering what the runtime for these operations are. They were all big O of log n. Well, that's not entirely true. It's not hard to imagine a scenario where a treep will take big O of n to search for an element. But since treeps rely on random values, we are concerned with the expected value of the runtime. And for a treep, the expected value for all of those operations will be big O of log n. I won't go over the analysis in this video, but here's a hint. If you sort every element in a treep based off of its priority value, and then inserted them into a regular binary search tree, it would have the same structure as the treep. And since the priorities are random values, then that ordering is a random permutation of the elements. In which case, the analysis for searching in a treep is the same as the analysis for searching in a random binary search tree.